So again, we're starting with 10.4, and then we're going to do 10.3 in a little bit. We'll start with finding the determinant of a matrix. So determinants can only be found in square matrices. So 2x2s, 3x3s. We don't do anything bigger than a 3x3 in this class, so just 2x2s and 3x3s. There's a lot of uses of determinants in other classes. So maybe if you go to college, you take a linear algebra class, depending on what you're going to major in, you might see those uses. But just for the sake of this class, you just need to know how to mathematically compute a determinant. So a determinant of a 2x2 matrix is just going to be the product of this diagonal. We call this the major diagonal, minus the product of the two numbers in this diagonal. So we call that the minor diagonal. Some ways that you can denote a determinant is like this, DET with an A. You could see it with two straight bars over your matrix A, or just straight bars over the entire matrix. But they all mean the exact same thing. I'll show you how to compute it in some examples. Okay, so we'll start with this first one. To find the determinant of this matrix, again, we typically use the straight bars to denote it. So I'm going to write in the straight bars a 2, a 1, a -3, and a 2. And again, the determinant of a 2x2 matrix is just the product of these numbers in this diagonal. So I'm going to write a 2 times a 2 minus the product of the numbers in this diagonal. So minus a 1 times -3. And so we just calculate these individually. So 2 times 2 is 4, minus 1 times -3 is -3. So 4 minus -3 is a positive 7. Your answer is always going to be a singular number. All right, simple enough? Good, right? So we'll try the exact same thing with the next one. To find the determinant of B, again, you can denote it with the straight bars. To save yourself a little bit of writing, you can write straight bars over the capital letter B. And once again, we're going to do the product of the major diagonal. So 2 times 2 minus the product of the minor diagonal, 4 times 1. So then we get 4 minus 4, which is 0. So then the determinant of this matrix is 0. In a few minutes, you're going to learn that if the determinant is 0, that means it is not invertible. So this matrix does not have an inverse. All right, I'll talk about that in a little bit, maybe like 10 minutes. All right, simple enough? All right, so try the next one. Okay, good. So again, the determinant of C is just the product of this diagonal, 0 times 4, minus the product of this diagonal, 2 times 3/2. All right, so then we get 0 minus 3, so -3. The determinant of matrix C is -3. All right, should be pretty easy. All right, 3x3s are a little bit trickier. I'm going to show you two methods of how you can do it. So this first method, so I'm going to say method 1, you might see this written as cofactor expansion. So let's say you're looking it up and you want to do a little bit more research. You might see this one as cofactor expansion. There's a lot of vocab in matrices. You don't really need to know what all of these mean. You just need to know the process. So what I like to do is, since this is a 3x3 matrix, I'm just going to write on the side a 3x3 matrix with alternating pluses and minuses. So I'm going to write a plus, a minus, a plus, a minus, a plus, a minus, a plus, a minus, a plus. And then what I like to do is I like to pick either a row or a column that looks like it would give you the easiest computations. It would be whatever has a 0 in it, just because you're going to see that you're going to end up, if there is a 0 in a row or a column, multiplying by a 0, which is pretty nice. So let's have a look. I'm going to pick, let's say, the first row, the very top row. All right, so this right here. We have a 0, a 2, and a 1. I'm picking this one just because it has a 0. And what I'm going to do is I'm going to look at what sign each entry corresponds with in, or what each entry corresponds to in this little matrix that I wrote right here. All right, so I'm going to go from left to right. Let's start at 0. What sign do we see there? There's a plus, so I'm going to write a positive 0. Doesn't really make a difference since it's 0, but just for the sake of consistency, that is a positive 0. And then this is going to be times the determinant of whatever is not in the row or column with 0. So I'm going to use these. This is the cofactor. Again, you don't need to know these words. So I'm going to multiply this by the determinant of -1, 2, 0, and 1. Again, I'm choosing those 4 numbers just because 0 has these numbers in its column and these numbers in its row, so you're picking whatever is not in that row or column. All right, so these numbers. All right, so it is a bit of a process. I'll show you again. I'm going to do the same thing with 2. All right, what sign do we see where the 2 is? A negative, right? So I'm going to write a -2. And then again, I'm looking at whatever numbers are not in that row or column. So in this case, it's the 3 and the 4, and the 2 and the 1. So it's going to be times the determinant of 3, 4, 2, 1. All right, and then I'll do the same thing with the 1. All right, what sign do we see where the 1 is? A positive, right? So there's a positive right there, so it's going to be a +1 times whatever is not in that row or column. In this case, it's the 3, 4, -1, 0. So we just kind of broke it up into smaller pieces. Now we'll just compute these. This first one is nice because 0 times the determinant is going to get you a number, right? So what is that going to get you? 0. That's why you typically are going to pick whatever has a 0 in it. And then you do the same thing with the next one. So I'm going to do -2 times, this is a determinant that we can compute, right? We just did it a few minutes ago. How do we find that determinant? The diagonals, right? So it's going to be 3 times 1 minus 4 times 2. What does that get you? -5. All right. And this is +1 times, we'll do the same thing here, 3 times 0 minus 4 times -1. Minus -4 is going to get you a +4. All right, and then we simplify this. So then we get, this is going to get you a 10, plus 4 is going to get you 14. So then that's the determinant of this 3 by 3 matrix. I can write it out. So it's going to get you 0 minus -4. Yeah, so +4. So that's one way to get the determinant. If you didn't like that, that's fine. I'll show you a different way. But first, are we okay with that?
Would that work with any row?
Uh-huh, yeah. So you can pick any row. If you see a 0 in the bottom row, you can do the same thing just as long as the signs are labeled appropriately. You can even choose the middle column, right? You can even choose that column. It works with any row or column. But only if you go that way. You can't really use a diagonal or anything. No, you could still do it. It just wouldn't cancel out nicely. But you can still do it. I'll do that with the next one also. So this one, again, I'm going to show you guys another method. Maybe you didn't like that one. So method 2. Again, if you want to do your own research, we can call this the rule of Sarrus. S-A-R-R-U-S. So this is a second method. To solve it using this method, I'm going to write the matrix as I see it. So 0, 2, 1, 3, -1, 2, 4, 0, 1. And then right outside of it, I'm going to write these first two columns exactly as I see it. So these first two columns right outside of it. So 0, 3, 4, and 2, negative 1, 0. Some of you might like this method a little bit more with the 3 by 3. But essentially, you're going to do the major diagonals, which the major diagonals, again, go this way, and the minors go this way. All right, so I'm going to do the major diagonals starting at 0. So I'm going to do 0 times negative 1 times 1. What does that get you? 0. And then I'm going to do the same thing with the next major diagonal. So 2 times 2 times 4. What does that get you? Good. 0 plus 16. Plus, I forgot to mention we're adding these. 1 times 3 times 0. 0, right? So this is our first part of it. And then I'm going to do minus the same exact process with the minor diagonal. So starting at the bottom, I'm going to do a 4 times negative 1 times 1. What does that get you? Negative 4. Same thing with the next one. 0 times 2 times 0. 0. And then 1 times 3 times 2. Good. And then we simplify these. 0 plus 16 plus 0 is 16. Minus negative 4 plus 0 plus 6 is 2. And then 16 minus 2 is 14. So we end up with the exact same answer, we just did it a different way. All right, you have to do a little bit more computation up front with this method, but you get your answer a little bit quicker. If you think you're going to make little mistakes, you might opt for this first method, right? Just because it breaks it up into smaller chunks.
For this method, we have to add 2 extra columns.
Yeah. So for this method, you need these on the outside. Yeah. The last one you just leave alone. All right. I'll do the same process with the next problem. So again, I'm going to show you exactly the same thing. I'm going to show you both ways, just so that you can decide which one you like more. So evaluate this determinant. Again, I'm just going to do method 1 first, and then I'm going to show you the second one. So again, this first method, I want to, on the side, just write out the signs. Plus, minus, plus, minus, plus, minus, plus, minus, plus. So just that on the side. You can pick any row, any column you want to. So just to show you that it works with anything, I'm going to pick this column. I'm going to pick that column. So with the 6, the 2, and the 4, I'm going to pick that one. What sign do we see where the 6 is? What sign is that? Positive, right? So then this is going to be a positive 6. And then I'm going to multiply it by the determinant of whatever is not in that row or column. So what numbers would those be? Good, right? So it's going to be this right here. Negative 3, 3, negative 1, 2. All right. Again, you're looking for whatever's not in the same row and column as that 6. All right, we'll do the same thing with the next one. What sign do we see where the 2 is? Good, right? We see a negative. So minus 2, and then what numbers are not in the same row and column as that 2? Good, right? 1 and 7, and then negative 1, 2. Same exact thing with the last one. What sign do we see where the 4 is? A positive, right? You're just matching them. So plus 4 times the determinant of whatever's not in that row or column. What do we see? This right here, right? So a 1, a 7, a negative 3, and a 3. All right, and now let's compute these. So this first one's going to be a positive 6 times, we're going to find the determinant of this 2 by 2 matrix. Negative 3 times 2 is negative 6. Minus negative 1 times 3 is plus 3. Same thing with the next one. We're going to do negative 2 times 1 times 2 is 2, minus 1 times negative 7. I'm sorry, negative 1 times 7 is plus 7. All right, we'll do the same thing with the next one. 4 times negative 21 minus 3. And then we just simplify this as much as we can. We get 6 times negative 3 minus 2 times 9 plus 4 times negative 24. So then we end up with negative 18 minus 18 hang on, plus, wait, or minus? Minus 96. Okay. Wait, which, okay, wait, hang on. Oh, yes. Okay. Yeah, I did that backwards. This should be flipped, sorry. It's like, I knew that's not the answer. Okay, 1 times 3 is 3. Okay, yeah, 1 times 3 is 3, minus negative 21 is plus 21. I did that backwards. So that should be a positive 24, so plus 96. Okay, good. Sorry about that. Okay, and then this is going to get you negative 36 plus 96 equals 60. Okay, yeah, that's correct. So then the determinant is 60. All right, so again, that's the first method. I'm going to show you again the second method, just in case you like that one more, for you to decide for yourself. All right, the second method, again, you're just going to write out exactly as you see it the first time. And then right outside is just going to be the first 2 columns repeated. So it's going to be a 6, a 2, and a 4, a 1, negative 3, and negative 1. And then you're just going to multiply the major diagonals. All right, so let's do 6 times negative 3 times 2. What does that get you? Okay, we get negative 36. We'll do 1 times 3 times 4, 12. And then 7 times 2 times negative 1, negative 14, good. And then we're going to do minus the second set of diagonals. So it's going to be 4 times negative 3 times 7. So we get 12 times 7, negative 84, good. And then we'll do negative 1 times 3 times 6, negative 18. And then we'll do 2 times 2 times 1, plus 4, good. And then we'll just simplify this. This is going to get you negative 24 minus 14, so negative 38. Minus, then we're going to get, well, I know this and this get you negative 80. Minus 18 is negative 98. And then minus negative 98 is going to get you plus 98, which is going to get you 60. So you get the exact same answer as we did before. We just did it a little differently. Again, choose whatever method you like best. If you're okay doing a bunch of multiplication up front to get an answer a little bit quicker, you can choose that method. If you want to be a little bit more careful, maybe you think you're going to make little mistakes here and there, you maybe want to pick the first method. It is a little bit more steps, but it's a little bit more careful. But it's up to you. Either one is valid. All right, so now we'll get to inverses of a matrix. So there's 2 types of problems that you'll see in this section, and it's determine if 2 matrices are inverses, and then it's find the inverse of a matrix if it's possible. All right, so for that first thing that I mentioned, to determine if 2 matrices are inverses, you're going to do matrix multiplication 2 times, and if you get this matrix both times, then they are inverses. All right, we call this the identity matrix. It's similar to if you have, like, let's say, I used this example last class, right? If I had 1 over x times x, right? 1 over x and x are inverses, so then this is going to get you just a 1. All right, this is the matrix version of a 1, let's say. All right. But to actually find and determine if these matrices are inverses, you need to multiply A times B and B times A. You have to do it both ways. Just because matrix multiplication is not commutative. Do you remember what commutative means? Like, as in, like, okay, if I had like 3 times 5, that's the same as what? 5 times 3, right? Matrices do not have that property. So you might not get the same answer both ways. You actually only get that if they are inverses, and they'll get you the identity matrix. So let's multiply these. So let's first find A times B. What was our process for multiplying matrices? So I'm going to do row times column. So row of the first times column of the second, and I'm going to go entry by entry. So I'm going to do -1 times 1. What does that get you? -1, good. Plus the second times the second. 2 times 1 is 2. All right. So then I'll do the same thing with the next column. All right, so I'm going to do first row, second column. And then I'll do the same thing, go entry by entry. What's -1 times -2? +2. And then you do the second times the second. So +2 times -1, which is plus -2. Good. All right. Let me erase. We'll do the exact same thing with the next one. So I'm going to do the next row. So second row times the first column. And this is going to get you -1 times 1, which is just -1. And then I'll do the second times the second, so +1 times 1, which is just 1. All right, same exact thing with the last row, last column. All right, so then I'm going to go entry by entry. I'm going to go -1 times -2, which is 2. And then 1 times -1 is -1. And then all we have to do is just simplify those. Do we get our identity matrix? We do. We get 1, 0, 0, 1, so it works this way. All right, so then I'll do the same thing using B times A. So now I'm going to use the rows of B times the columns of A. All right, so I'm going to use this row times the first column. And then again, go entry by entry. We're going to do 1 times -1, which is -1. And then -2 times -1 is a +2. All right, same thing. First row, second column. It's going to get you 1 times 2, so 2. Plus 1 times -2, which is -2. All right, same exact thing with the next. I'm going to use the second row, first column. So we're going to do -1 times 1, which is -1. And then -1 times -1, which is a +1. Same exact thing with the last row, last column. I'm going to do 1 times 2 plus 1 times -1, so -1. And then does this get you the identity matrix? It does. So then these are inverses. So when it says show that these are inverses, you're just showing that word. All right, so the next part of it is to find, you're going to find by hand the inverse of a 2 by 2 matrix. I'll show you 2 examples, and then that'll be it for today. But to find the inverse, you're going to switch the numbers on the major diagonal, and then you're going to change the sign of whatever's in the minor diagonal. And then you multiply each entry by 1 over the determinant. So we just learned a little bit ago that this on the bottom, 1 over that number, that is the determinant of a 2 by 2 matrix. So this is your determinant. All right, so I'll show you how to do that with this example. First, let's find the determinant of A. All right, how do we do that again? Good, right? So we're going to do this, 3 times 2 minus 2, negative 2 times negative 1, so 2. So this is 6 minus 2, so 4. So our determinant is 4. All right, that's going to help us in a bit. And now to actually find the inverse, it's going to be 1 over that number times whatever you get when you switch these numbers in the major diagonal and then change the signs in the minor diagonal. So we're going to have A inverse is the same as 1 over the determinant, which is 4, times flip the major diagonal, so 2 and 3, and then change the signs of the minor one, 1 and 2. And then you multiply. This is a scalar multiple now. You're just going to multiply each number on the inside by 1/4. So A inverse is we're going to end up with 1/2, 1/4, 1/2, and 3/4. So this is our inverse. All right, are you okay with that? Should be pretty easy. We only really, in this class, find the inverse of 2x2s, so you don't really need to worry about a 3x3. Really, for a 3x3, we might just ask to find the determinant, and then what we're going to do on Thursday, maybe, with Cramer's rule, and solving systems of equations with matrices. All right, so let's try this one as well. All right, this is a good one to try. Let's first start with the determinant. So what do we get? 3 times 2, right? Minus negative 6 times negative 1. 6, we get 0. So here's a fun fact. When the determinant is 0, this is not invertible. You cannot take the inverse. So you would just leave it alone like that. This is not invertible. And just for the sake of your notes, I'm just going to say because the determinant is 0. Is 0. All right, so that's the only other case that you might run into, is you first need to find the determinant, and if it's a non-zero number, then you have an inverse. But if it's 0, just because when you go to plug it into your formula, 1 over the determinant, you get 1 over 0, and that doesn't make sense. All right, so you wouldn't do anything with that. You would just say it's not invertible. And then notice the directions say it's possible, right? So it's not always possible.